Hi, this is Professor Stugard, and in this video lecture, we're going to be talking about some vector basics. Now, given your background, you might know some of this stuff already, and this might be more of a review, but let's make sure we're still on the same page with all of our notations and definitions. So first of all, well, what is a vector? Well, before we get to that, let's talk about what a scalar is, because those are the two quantities we're really going to be discussing quite a bit in our multivariable calculus course. So a scalar is any single quantity that we use to denote size or scale. So weight or time or even the number of pencils on my desk right now, those are all scalar quantities because they give me information about size or scale of something. Now a vector is a little different because a vector is defined not just by its size or scale, but also, in addition, it's defined by its direction. And so the most common example is velocity. Now, velocity is a vector where your speed is your magnitude. That's how fast you're going. But velocity, we also need to have our direction defined. Are we traveling north or east or, well, northeast? And so for that reason, because a vector has those two parts, it has that scalar, it has its size or its magnitude, but it also has its direction. We commonly refer to our vectors as directed quantities. It's a size or quantity that is directed in a specific direction. Now, in standard position, we usually consider our vectors to have their tail or their initial points at the origin. And this is true whether we're in 2 dimensions, as in this image, or in 3 dimensions. We still consider standard position to be when the vector has its tail at the origin. Then the arrow, the length of the arrow, corresponds with its magnitude, and, well, the direction is kind of given by that arrow. And in 2 dimensions, we can see here that that direction can actually be given by a single angle, and is actually related to polar coordinates, which you probably want to review if you're still a little rusty on those. Now, there are lots of different notations for vectors because vectors are incredibly useful in many different areas and disciplines. Now, typically, though, when we define a variable as a vector, to differentiate it from a scalar, we either denote it in bold, and that's what your textbook does, and that's what lots of textbooks do, is they use vectors as bold, or you can put an arrow over top. I am almost always going to put the arrow over top, and especially when I'm taking notes or I'm doing work, I am always going to put that arrow over top because I need to make sure I differentiate between my scalars and my vectors. And because my pencil, when I'm taking notes, does not have an option to write in bold, the arrow over top is the easiest way to do it. And you want to make sure that you are absolutely being disciplined and putting that arrow over top for your vectors, just so you don't accidentally make little mistakes and get an entire problem wrong because, well, you accidentally considered a vector to be a scalar or vice versa. Now, in mathematics, we're going to probably most commonly express our vectors in what's known as component form. So, component form for a vector consists first of these triangle brackets. So, if you see these triangle brackets here, that's how we're going to denote that what we're talking about is a vector. If it's parentheses, that's an ordered pair. But if we use the triangle brackets, that is absolutely going to denote that we're doing a vector. And then what we do with our vectors is that we have each part or each component separated by a comma. So in this case, my vector v, the first number is 4, so my x component is 4, comma, then my next number is 3, that becomes my y component. I could add more components on as I wanted to. I can add as many components as I wanted. If I add my next one, it would be my z component, and so on. But typically when we do mathematics, this is how we're going to represent our vectors. Now geometrically, if we put this vector in standard position, we would represent this in the xy plane as, well, this arrow. And the really nice part about this standard position is that my vector v, which has an x component of 4 and a y component of 3, when I put this in standard position, the terminal point, or the tip of my arrow, points to the ordered pair, well, 4, 3. And it's a convenient way for us to kind of go back and forth between these two ideas in space or on my plane, where, again, my x component is 4, my y component is 3, And as a vector, obviously it's this arrow in space, it's this directed quantity, which is going to point to my ordered pair 4, 3. And again, just be careful about the notation. And again, be very, very careful when you're doing your notes to make sure that your vectors really do have triangle brackets, whereas your ordered pairs are still the parentheses. Again, handwriting counts at this point in your mathematics career. Now, there's other ways that we represent our vectors as well. Another very common way that we're going to represent our vectors is using a standard basis, where we have 4i plus 3j. And again, it should seem fairly straightforward and intuitive that, we're talking about x's and y's and components, but this time it's i's and j's. And we're going to go more in depth with what the standard basis is a little bit later in this video, but it is going to work fairly intuitively. Now, in linear algebra or computer science, we typically represent our vectors as a matrix, or as a single column matrix, really, where we would store our values this way, using those square brackets. And again, that's a perfectly valid way to do this. And if you've taken linear algebra already and are very comfortable with the notation, you could actually do this entire course in multivariable calculus using that notation, and you'll be just fine. The last way we represent vectors is if I'm trying to describe the displacement, and vectors are very good for displacement, between 2 points, instead of necessarily just at the origin, we can say our initial point P and our terminal point Q, and then we use this notation, well, PQ. We still have the arrow over top, and again, it's going to point towards the terminal point, and again, that order matters. Now, we are going to use the geometric notation. We're going to be drawing arrows quite a bit to help develop some of our intuition about these mathematical concepts involving vectors. But all of our rigorous mathematics, any proofs or questions on exams, we are going to have to actually use the component form or the standard basis form to be able to, show that something is actually true or to prove it. So we're going to have to be comfortable with both ways that we represent our vectors. Now, one of the first important qualities about a vector is its magnitude. And so the magnitude of a vector is also its length. And we're going to find the magnitude of our vector by applying the Pythagorean theorem to that vector in standard position. So if I'm given a vector in 3 space, given by the components a, b, and c, the magnitude of that vector is going to be given by, applying the Pythagorean theorem to this, that 3-dimensional Pythagorean theorem. So that's going to be the square root of a squared plus b squared plus c squared. And the magnitude is denoted with these straight up and down lines on either side, which is actually our absolute value notation, because absolute values really are the magnitude. When we do an absolute value of a number, say, what's the absolute value of 3? Well, it's 3, because it's 3 units away from the origin. And again, that's where that standard position comes in. If I have a vector in standard position, I want to know the distance from the origin to that point. Well, I apply the Pythagorean theorem. Now, the one thing I do want to note is that in many other textbooks, to denote the difference between a scalar and a vector, a lot of times they'll put the double bars around a vector to denote its magnitude instead of just the single absolute values. That's not what our textbook does, so that's not what we're going to do. And besides, like I said, the absolute value is really what we're looking at with magnitudes. It's the same concept, except instead of doing the absolute value of just a number in 1 dimension, going across just my number line, we're now going to look at the absolute value or the distance in 2 dimensions or 3 dimensions, or you could even apply to as many dimensions as you'd like. So for our first example, let's find the magnitude of that vector we were talking about before, the vector given by the components 4, 3. Well, we're just going to apply the formula. The magnitude of v is going to be the square root of 4 squared plus 3 squared. So that's 16 plus 9, which is 25. The square root of 25 is 5. And so the magnitude of my vector is 5. And again, if we go back to the image, that should make a lot of sense, because what we really had here was a 3, 4, 5 right triangle, where one side of the triangle was 3, one was 4, and then obviously the hypotenuse, which is my magnitude of the vector in this case, is going to be 5. quick definition, the zero vector. So the zero vector has no displacement, or it has a magnitude of 0, and it's denoted with, well, 0 with a line over top of it. And each component of the zero vector is going to be 0. So in 3 space, the zero vector is, well, 0, 0, 0. I do want to make a point here to make sure that if you're talking about the zero vector, you have that vector notation above it. The zero vector and the scalar 0 are very different ideas. And you don't want to get lazy and not write that little arrow over top when you're doing your work and accidentally, well, confuse your vector for your scalar. So now basic vector arithmetic. So 2 vectors are equal if they have the same magnitude and direction. The position of the vector does not matter. Now this can be a little hard at first intuitively, but it's this kind of same idea as, well, with scalars, right? I can say if I have 3 apples and 3 oranges, obviously they're different objects. One's apples and one's are oranges, but they have the same scale or the same size. I can match them up 1 and 1, and their size is the same regardless of, well, what the actual item was. Or if it was 3 pencils, same idea. And that's the same idea with our vectors. So again, it's not intuitive at first, but as long as the vector has the same magnitude and the same direction, they're the same. So this vector over here is equal to that vector over there, which is equal to all of these vectors in between. We can move a vector anywhere we want in space, and it's still going to be the same vector. They're still equal to each other, no matter where we place it. Now, adding vectors. So since vectors are typically used to denote displacement, or getting from point A to point B, when I add 2 vectors, their sum is, well, the same as going from point A to point B to point C, or, well, really, we don't care necessarily about the path they traveled, we just care about going from A to C. And so when we add 2 vectors, it essentially, well, becomes the hypotenuse of that triangle. If I add u plus v, then I can make a triangle out of it, and u plus v will be, well, like I said, that third leg of my triangle. Now back to that idea of being able to move vectors around, if I switch their position around and put both vectors u and v in standard position, and then actually make copies of them, I can create a parallelogram out of any 2 vectors. And this concept is going to be very important. We're going to see it pop up quite a bit in a lot of future sections where we take 2 vectors, and from 2 vectors I can create any parallelogram, or, well, I can create a parallelogram out of my 2 vectors. And from moving it around, hopefully we take a look at this picture, we can see that by moving these vectors around and creating a parallelogram, that sum of the 2 vectors, u and plus v, or v plus u, because I can go in either order, ends up being the long side of that parallelogram. And again, it might take a little bit of time for that intuition to get there for this, because it is kind of strange to be able to move things around in space and consider them equal, but it is very important. Now, to actually do this mathematically, to add 2 vectors, it is incredibly easy, because all I need to do to add 2 vectors is essentially add their components. So if I have vector u in blue and vector v in brown, and I want to add them together, u plus v, well, take their first 2 components, the 3 and the 2, and add those together, 3 plus 2. And then do the same thing with all the other components, the 7 and the -1, the -5 and the -6. Add each of the components together, and so u plus v should end up becoming 5, 6, -11, because it's 3 plus 2, then 7 plus -1, then -5 plus -6. Again, just go component by component. It's fairly easy and fairly intuitive. To use the standard basis form, again, this is really nice and convenient because it's really just like combining like terms. So the standard basis form, my vector u would now be 3i plus 7j minus 5k, and v would be 2i minus 1j minus 6k. And when I add them together, I just, well, combine like terms. So combine the i's, 3i and 2i, combine the j's, 7j and minus 1j, combine the k's, -5k, -6k. And we end up with 5i plus 6j minus 11k. And again, it's just another way of doing the same problem, and it is fairly intuitive to do that sort of addition. Now, scalar multiplication of vectors. Now, we can multiply any vector v with a scalar c, and then the product is just, well, c times v. And what's going to happen is that we still have we have a new vector that's going to be going in the same direction, or is parallel to my vector v, but now its magnitude is going to be scaled by, well, the scalar c. And so the nice thing is that, again, in practice mathematically, we just can distribute that scalar through to every component of my vector or factor it out. So my example 3 down there, 20, negative 30, 15, well, they're all multiples of 5. I can absolutely divide each of those by 5 and factor it out just the normal way I do factoring. Now, geometrically, when I multiply a vector by a negative scalar, that means that vector is going to point in the opposite direction. And so I have a couple examples here. So vector v, 2v means, well, it's going to be going in the same direction, which means the tip of the arrow is still pointing in the same direction. It's just twice as long. 1/2 v, again, same direction, but half as long as v. Minus v means that now I'm going in the opposite direction. So this is still parallel, but now it's going in the opposite direction, facing the opposite way. And I can even do negatives with other scales too. So negative 1.5v, again, the opposite direction, but now it's 1.5 times as big and in the opposite direction. So subtracting vectors. When we subtract vectors, well, what I'm really doing is adding two vectors, except that second vector is flipped in its opposite direction. Now, subtracting vectors in component form is really intuitive, and it's the same as adding vectors. You just go component by component. You should be able to figure that out without any issue, really. But the geometric interpretation of subtracting vectors can be a little bit more confusing, and it is something that's going to show up again. And so let's actually take a look at how I would subtract vectors using that geometric kind of notation. So let's start off with, again, our vectors u and v in standard position, which means their tails are together. And now I want to subtract u minus v. Well, minus v just means v is in the opposite direction. So I'm going to take v in the opposite direction with the tail on the other end, and I'm going to, well, connect that tip to, well, the tip of u to the tail of minus v. And then again, all I care about is the displacement, or the overall place we end up. So u minus v is, again, starting at the origin, and, well, where did I actually end up? There's my u minus v. Now, when we talk about subtracting vectors, the part that can get a little confusing is that, again, I can move these vectors wherever I would like in space. So I'm going to move my u minus v vector up. And now move it in position with my original vectors, v and u in standard position, erase all of my work. And now this is how we typically represent the subtraction of two vectors in space. And so again, if you see this image of the triangle, well, there we go. U and v in standard position. U minus v is, well, again, the third leg of this triangle. And just pay attention, note the way that it points, right? The tip of the arrow of u minus v is going to be pointing at the same place as the tip of u. Now I can build my parallelogram again. Again, make another copy of v, another copy of u, make a parallelogram, and notice that u minus v is now the opposite diagonal from the sum. So remember, the sum of u plus v was the diagonal going the long way, this way. U minus v is now the other diagonal. All right. And again, just take a minute with both of those interpretations and make sure you kind of understand how we got there and why. Another incredibly important topic when it comes to vectors is unit vectors. So unit vector is just a vector whose magnitude is equal to 1. And that's going to be very useful, especially when we do calculus, because we want to make sure a lot of times that things have the same scale. We can't really compare things. We can't compare two vectors unless they have a similar scale or some standard way that we can kind of start with. And unit vectors are going to be the way that we do this. And so being able to take a vector, preserve its direction. So if I have a vector v and I preserve its direction, I want it to be in the same direction as v, but to have a unit length, all I need to do is divide that vector by its magnitude. And again, that's a scalar quantity equal to its magnitude. The way I would do that in practice, here in example 4, is if I'm given that vector 4, 3, and I want a unit vector u with the same direction, well, find the magnitude. We found the magnitude of this one earlier. Use the Pythagorean theorem, the magnitude is 5. Then the unit vector u is going to be 1/5 times my original vector, or well, divide each of the components by 5. So 4/5 and 3/5. And that is going to be a unit vector that is in the same exact direction as my original vector v. We can even check this very quickly using the Pythagorean theorem. So go ahead, do 4/5 squared plus 3/5 squared, take the square root of that, and it's absolutely going to be equal to 1. All right, now let's talk about the standard basis vectors. So we saw how easy it is to actually use standard basis vectors to do vector arithmetic, but what are they actually? Well, the standard basis vectors are all unit vectors that represent moving one unit along the coordinate axes. So the I vector, or typically we call these hats, so I hat moves one unit along the x-axis, j hat moves one unit along the y, and k hat moves one unit along the z-axis. And so when I represent just a typical vector like 2i minus 1j plus 6k, what's really going on is, well, I've kind of simplified things to make math easier, but what's really happening is I can actually do my scalar multiplication and I can do my vector addition and subtraction and see that it's really the same way that I represented my vector in component form. And so we can do this very quickly. So if I replace my I with my I vector, and so the I vector has a 1 in the x component and then zeros everywhere else. And so again, we know how to do the scalar multiplication. We just distribute. And we do the same thing with the other vectors. And so j hat has a 1 in the y component, and k hat has a 1 in the z component. Again, distribute. Now we get 3 vectors. Add those vectors, and again, we add component by component, but obviously 2, 0, 0, well, there's lots of zeros, so everything's going to be 0 except for that one value. And we see that's really the same way as saying vector in component form 2, negative 1, 6. And again, it's really, really easy to jump in between these. You never actually have to do this work out. I just wanted to kind of show you how these things work and I'll kind of recap our scalar multiplication and addition or subtraction. So, as we start to sum up some of these properties of vectors in, well, vector arithmetic, if I have vectors a, b, and c in some vector space, Vn, and then c and d are scalars, we have all these properties. So the first property, property 1, is the commutative property. That means a plus b and b plus a are the same things. I can add them in either order, and we kind of saw that as the diagonal of our parallelogram. But that's the commutative property. I can add them in either order, so that's really nice. Property 2 is the associative property, which means if I have 3 vectors, I can add those 3 vectors in any order and still get the same result. Number 3 is our identity property, the additive identity, meaning that if I add the 0 vector, it's not going to change it. If I have a vector a plus the 0 vector, I still have vector a. It does nothing. The identity is really your do nothing. Property 4 is the inverse property, meaning that there's something that we can do to get back to the identity. And again, a plus minus a is going to get us back to 0, which is our identity, which means that an inverse exists. Property 5 is the distributive property, which means I can distribute a scalar through to vector addition. Property 6 is the distributive property, except this time I can distribute a vector through to the sum of scalars. Property 7 is the associative property, but this time with scalars. Again, you can multiply the scalars in any order. And then property 8 is another identity property, but this time the multiplicative identity, because multiplying by 1 does nothing, which means 1 is your multiplicative identity. It's your do nothing. The last topic that we want to talk about, though, when we're describing vectors, and in particular two vectors, is the angle between those two vectors. So if I have vectors u and v in standard position, which means their initial points are at the origin, the angle theta is going to be the angle between vectors u and v. And it's going to be the smaller of the angles formed, which means it has to be bounded between 0 and pi. So what that really means is that obviously I have these two vectors. Here's my angle theta. Well, I could consider this big giant angle on the other side, but no, we're not actually going to do that. We're only going to consider the smaller of the two angles formed, and that defines our angle theta. So that means that if two vectors are scalar multiples of each other, that means they're going to be parallel. So parallel vectors means that they either have the same direction, meaning theta is 0, or the opposite direction, theta equals pi in the opposite direction. So those vectors that we looked at earlier, all that scalar multiplication, each one of these vectors are parallel. They're all parallel to each other because they either face the same direction or the opposite direction. So the last example, how can I tell whether or not vectors are parallel? Well, they need to be scalar multiples of each other. So what I'm going to do is I'm going to factor each of these vectors and we'll see what they look like. Well, if I factor A, 3, 6, they have a common factor of 3. And vector B clearly has a common factor of 5. And if I factor that out, vector A is really 3 times the vector 1, 2. And vector B is 5 times the vector 1, 2. And so they're both scalar multiples of the same vector 1, 2, which means they have to be parallel. They actually point in the same direction. All right, so that covers some vector basics. Again, take your time, work through the homework, and if you have any questions, let me know, because we're going to be using these vectors throughout the entire multivariable calculus course. So making sure you have a strong foundation now is going to, well, make life a lot easier for future you. So good luck on the homework. Email me if you have questions. Good luck.